star W. Welcome to the week 10 live session for the GPU architecture and programming course. Let's get started. So today again we will have a quick recap of week 10's course contents followed by the problem solving. So in week 10, week 9 was the introduction to OpenCL. We went a little deeper into OpenCL in week 10. So we looked at various things like the command queues and devices. We looked at multiple device programming, things like partitioning a kernel, how do you sort of partition a device, which is device fission, and we looked at concurrency. So in terms of concurrency, we looked at concurrency from OpenCL perspective, where we looked at how do you execute a concurrent kernel. From the CUDA perspective, we also looked at streams, which is the mechanism for concurrency in CUDA. We also looked at synchronization from that perspective. So we'll do a quick recap of this, and in case there are any questions on any of these topics, feel free to ask on the discussion forum. Okay, so heterogeneous computing, again, like we've been talking about OpenCL from the past week itself. OpenCL is primarily intended to support not just GPUs but a variety of heterogeneous devices, and there are a lot of platforms or sort of so in this course we use device to mean either a CPU or a GPU, so we'll stick to that. So let's think of a system or a computing platform where you have more than one kind of device, right? So for instance, the Jetsons that were spoken about, I think in the week 2 or 3 from NVIDIA, they are one of those heterogeneous computing platforms where you have a multi-core ARM CPU, you have a GPU, you have some other custom processors as well. So these are typically referred to as heterogeneous platforms. And heterogeneous computing utilizes this heterogeneity. Basically, you have different kinds of compute available, and you use this different kinds of compute efficiently to gain performance or energy efficiency. That's the idea behind heterogeneous computing. Now, concurrency is when applications execute functions concurrently on multiple processors. So suppose you have a CPU and a GPU, there's nothing stopping me from using both of them. Of course, there may be some things that come into play. For instance, if the RAM is shared between the two, you may end up with some memory contention, right? Things like that. But concurrency is broadly based on the idea that you execute on multiple processors. And OpenCL, as we spoke, is an ideal programming language uh, for heterogeneous computing implementation because it supports programming from multiple computing devices, CPU, GPU, FPGA, and so on. Okay, so with that, so yeah, so the idea is, like I said, you should be using all the available processors or the compute that's available on the system efficiently. So what are some of the challenges that come with doing this, right? So for instance, if you have a given task, how do you decide which device to run it on? Or how do you decide how to partition the task? And then how do you minimize the overhead of data transfer? Because you have to transfer data to each of these processors, you have to synchronize and things like that. And again, if you're able to do this well, you will gain either performance or energy benefits. But these challenges need to be handled in an efficient manner. So here's an example. So this is one platform or a system where you have two CPUs from AMD and a GPU from AMD and also a GPU from NVIDIA. This is probably a little rare, but many cases when you have systems with integrated GPU, so you'll see that even though you have a discrete card from NVIDIA, you also have an integrated GPU, most likely from Intel, right? So this sort of a scenario is possible. So now, as we studied in the previous week, you group devices from a given vendor into a single platform or a context, right? So these three go into platform 1 and these two go into this one, NVIDIA GPU goes into platform 2 and therefore context too. Again, the way you create context for these devices can be different. This is just an example. We will study some of the different ways you can create context. So here, now this platform, as we said, has these three devices. So the blue are the CPUs and the orangish yellow is the GPU. So this is device 1 to these are your three devices and they are mapped to command queues. So in this example, each device is mapped to a different command queue, and then you have this NVIDIA GPU mapped to this context and this command queue. So now let's go into the details of command queue, right? Last week we studied that a command queue can be associated with only one device, but this week we will study some of the other details, right? So if you have a single device, it can be associated with a single command queue. This part we've already gone through. A single device may be associated with multiple command queues with the same context. This is also a possibility. And a single device may be associated with multiple command queues associated with different contexts also, right? So these are the three possible single device use cases. Simplest one, which we saw in the previous example, single device, single command queue. Second form, single device, multiple command queues, but remember that it would be in a single context. Third one, multiple command queues, multiple contexts, right? We will see what's the point of doing some of these things, but for now, these are the three ways you could handle single device. Now coming to different devices may be associated with multiple command queues within the same context. Again, this depends on how you create the context. It also depends on the hardware vendor and things like that. Now, the other mode you have is different devices, multiple command queues, different context. So same context, different context. So yes, since a command queue can be only associated with one device, you cannot have the third combination with different devices and multiple command queue. So that's just two possibilities. Okay, so now let's go into the details of some of these. Why or what's the use of doing this, right? There are different ways of doing things, but when would you use one particular way? So multiple command queues with same context in a single device, right? So here what you do is you take multiple command queues and map it to the same device. Why do you do this? To overlap execution of different commands or overlap commands and host device communication, right? So you basically have one single device and you map it to two command queues. You enqueue different commands into both of these queues. So what happens is, if these commands can by inherently execute independently, for instance, let's say one of these is a compute command and one of these is a host device communication, right? So those two can happen independently, and by putting them in different command queues, you are allowing for that independent execution. That's the primary reason why you would do this. So applications would queue multiple independent commands without needing synchronization as long as the objects are not being shared, right? So these are not dependent in any way, right? Then you can do this. Now, multiple command queues with same context in single device, right? So again, independent streams of computation. We assume 3 independent tasks that need to execute on a device. So you would have 3 command queues with tasks enqueued in each of them. Then you can form this sort of pipeline such that the device is executing the kernel code while I/O is being performed. This achieves better utilization by not having the device waiting idly for data. So this is again why you would do that. Yeah, now we'll go to the next example. Multiple command queues with different contexts. So you can also create multiple contexts. Now the question is why. So in the previous example, with the same context and multiple command queues, it's basically to gain benefits of executing multiple things, right? Here, why do we do it? Typically, it has no benefit. but it may be useful when an application that uses OpenCL for some operations also uses a third party which internally uses OpenCL for some algorithm. So you may want to create a context level separation, but it does not have any benefit in execution time. Okay, so those are the single device use cases. Now we will go to multi-device programming. So multi-device programming has two execution models. They work in a pipelined manner where one device waits for the results of the other, right? So this is the same pipelining idea that's there in computer architecture that we have maybe discussed even in this week in concurrency, and maybe in an earlier lecture, maybe week 0 or week 1 in the computer architecture refreshing. Or the other way you could use two devices is both of them work concurrently and independently of each other. So now we will look at the different device scenarios. So you could have multiple command queues with the same context. So if you have a CPU and a GPU or multiple GPUs, each device needs its own command queue. That's by definition of how a command queue is associated with the device. Now, the standard way to work with multiple devices is creating a single context. Why is that? Because as we earlier also went through, memory objects are globally visible to all devices within the context. Event is only valid in a context where it's created. So these are the two things you have to remember about a context. These are contextual properties. So the standard way is to use a single context and multiple command queues. Right now, we look at concurrent kernel execution. So again, like we discussed, the definition of concurrency is where a set of tasks can make progress at the same time. And I think we went through the difference of concurrency and parallelism in an earlier lecture, so you have to keep that in mind as well. So how do you do this? Again, in OpenCL, you need to identify the concurrency in your problem and efficiently schedule it. And the concurrent tasks that can be running different kernels from independent applications, different kernels without dependency between them, partitioned instances of the same kernel. So these are three different examples of concurrent tasks, right? One is you have completely independent applications. Second is, like we saw before, you could have kernels in from the same application but without dependencies. Third is you could partition a kernel, right? These are three different ways of achieving concurrency. So now when it comes to partitioning, so we have multiple devices. How do we partition a kernel, right? Or do we even partition a kernel? So first you need to be aware of whether a kernel is going to be performing much better on CPU or GPU, right? The kernel's characteristics could decide that, right? For instance, does it have a lot of divergence, and or does it have a lot of parallelism inherently, and this is very GPU friendly, right? But if you execute a kernel on one particular device, the challenge with heterogeneous computing platforms is that the other available devices on these platforms may be idle. So you're in some sense losing out some performance that you can gain from them. So then you think, how do I get better performance and also utilize all of these devices? So partitioning is the technique that is used there. So what we do in partitioning is we kind of partition this kernel and split it across multiple OpenCL devices. When I say split the kernel, one way to do it is to partition the data efficiently. So remember, we went through different kinds of parallelism in one of the lectures: data parallelism, task parallelism. So one of the ways to do this with a kernel is to partition the data and distribute it across multiple devices. You launch the same kernel, but it now operates on partitioned data. And these partitioned kernels can run concurrently, reducing the total execution time. So here's a pictorial example, right? So you have a CPU and a GPU, and so now the choice you have to make here is how much data, or what is your partitioning ratio between the CPU and GPU. So in this case, you can see that the majority is given to GPU and very little is given to CPU. Again, right, typically this is the case for most kernels. GPU would be very, very efficient. Because why do you do this? If not, let's say I did a very naive half partitioning, right? I give the same amount to both of them. So then, and then I launch K1, right? This is what the diagram looks like. The GPU finishes off at this point, and the CPU is going to take a lot longer to finish up the same amount of data for this kernel. So as a result, you have the GPU just sitting idle waiting here, and your kernel is complete only at this point in time, which means that you haven't really reduced the execution time, because let's say if you ran it only on the GPU, it may have finished at this point, right? So now you may ask yourself, is partitioning helping me at all? Because my execution time was earlier this much, now it's become this much, which is technically worse, right? So that's what we studied. We have to partition smartly if you need to benefit from heterogeneity. So look at this partitioning scheme where I give very little to the CPU. Basically, I give the CPU how much ever is needed so that both of them can finish at the same time, right? So now the reduction in execution time may be very little, right? This might be what it takes to execute standalone on a GPU, and you are reducing it to this. But there may be other benefits also that you gain. For instance, a GPU consumes a lot more power, right? So you may be saving energy, a lot more energy in this amount of time, and overall you gain some benefits in execution time, right? So this is smart partitioning. It's kind of balancing your workload so that both of them take the same time. So you don't give equal amounts of workload to both. Instead, you partition such that both finish at the same time. So this is the idea of partitioning. Now we look at concurrency from a CUDA perspective. Again, the idea is the same. Applications must execute functions concurrently on multiple processors so that they can be used efficiently. CUDA applications manage concurrency by executing asynchronous commands in streams. So, and a stream is, you can think of it as a sequence of commands that execute in order. Different streams may execute their commands concurrently or out of order with respect to each other. So the stream is kind of a primitive that CUDA offers to you, and you can use this to achieve concurrency. So CUDA stream refers to a sequence of asynchronous CUDA operations that execute on a device in the order issued by the host code. These operations can include host device data transfer, kernel launches, and most other commands that are issued by the host but handled by the device. What does this mean? So I launch a kernel that is done from the host side, but the kernel is actually executed by the device, right? So that's what this means. So the execution of an operation is always asynchronous with respect to the host, in the sense that if I launch a kernel, I have no control over when that kernel will actually be executed. The kernel launch will return to the host immediately. It is not synchronous. So it is a programmer's responsibility to use the APIs to ensure that the asynchronous operation has completed before using its result. So if I, for instance, execute something in a kernel and I try to read the result before that kernel has finished executing, I may get a wrong result, right? So it's the programmer's responsibility to ensure that you get the right result or the operation has completed. Okay, so now what are the different streams that are available to you, right? So all CUDA operations, whether or not you specify a stream, either explicitly, so I could say run this on stream 1, stream 2, or I don't say anything. Regardless of which one you use, it always runs in a stream. So there are two types of streams: implicitly declared stream, which is null stream, meaning that if you don't specify a stream, it runs on the null stream. If you explicitly declare a stream, a non-null stream, it runs there. So null stream is like the default stream that kernel launches and data transfers use if you don't specify something. All CUDA examples discussed previously, everything that you saw from week 1 to week 9, previously used the null or the default stream. So how do you exploit concurrency? So asynchronous stream-based kernel launches and data transfers, enable the following types of coarse-grained concurrency. So you could overlap host computation and device computation, host computation and host device data transfer, host device data transfer and device computation, concurrent device computation. So these are various. So basically there's computation and data transfer, right? And depending on where the computation happens, you get this many combinations. So here's an example, a pictorial example of concurrency. So if you did it serially, there is a memory copy from host to device, then there is a kernel execution, and the memory copy, basically the result, is copied from the device to the host. So this x-axis is time. So this is the amount of time that this serial execution takes. Now if I do this concurrently, then what happens, right? So there is a host to device transfer, then the kernel starts executing. By the time this host to device transfer finishes, I start the host to device transfer of the next kernel, right? And then similarly, once this kernel completes, I am free to start its device to host transfer, right? And so on. So this is your typical pipelining example, basically with a 3-stage pipeline where you have host to device, kernel execution, and device to host, right? And you get a performance improvement in time because you're doing this. Now, a few things to keep in mind with data transfer operations is that they may not be executed concurrently even though you call them in different streams, because there is a shared resource underneath, right? So again, remember those levels of abstraction we discussed. So there are some things that are available from a hardware perspective and some things that are available from a software perspective. So stream is an abstraction that is defined at a software level, but the underlying hardware resource in this case is the PCIe bus. So if you have a duplex PCIe bus, then they can overlap two data transfers with the condition that they are in different streams and in different directions. So for instance, you could overlap a host to D transfer with a device to host transfer, right? This is possible, but only with a duplex PCIe bus. You cannot overlap two host to device transfers even in this case, right? So ultimately what you can achieve is limited by your hardware also, regardless of what software primitives you use. Okay, with that, we come to the problem solving session. Again, like I said, if you have any other doubts, please ask in the discussion forum. And we will have only 2 more live sessions, week 11 and week 12. So make sure to get any of your doubts cleared, right? Any week's content, for instance, if you have doubts, please feel free to ask it either in the live session itself or by posting on the discussion forum saying that you would like this discussed in the live session, because soon after that you will have your exam. So make use of these last 2 remaining live sessions. We will resume with the problem solving in a minute. So here's what I'll do. Even though there's no one in today's live session, I will read the question and give you 1 minute or 2 minutes depending on the problem. So you can watch the video, solve it, and then look at the answer. Suppose an application uses OpenCL for certain operations and also uses some third-party library that happens to use OpenCL internally to accelerate some algorithms on a single OpenCL supported GPU. What will be the preferred choice for context and command queues in such a scenario? Single command queue with single context in single device, single command queue with different context in single device, multiple command queues with different contexts in single device, multiple command queues with the same context in single device. So this is just a single GPU, right? So all the options say single device. You have to figure out which one is useful in this context. Okay, let's look at the answer. So the answer is multiple command queues with different contexts. And again, this is something we already discussed. So we, for a single device, we looked at having a single context with a single command queue, which is the simplest one. We also looked at multiple command queues with the same context. Single command queue with a different context doesn't even make sense, so we will rule this out. In this context, we are not trying to gain concurrency, we are trying to just get a different context for two of these use cases, right, for a logical separation. So C is your right answer. You can look back at the lecture notes if this is not clear. We'll move to the next one. What is the advantage of implementing multiple command queues within the same context in a single device for an OpenCL code? Helps in faster data processing by improving synchronization, reduces kernel launch overhead by having multiple command queues, pipeline can be formed for better utilization by not having the device sit idle waiting for data, improves data sharing across multiple command queues in the same context, thus improving performance. Okay, let's take a look at the answer. So C is the right answer. Let's think about why that is. So again, this is a single device. We're talking about same context but multiple command queues. So why do you do that? Primarily to have independent things. So if you have two command queues and you queue up commands that don't need any synchronization, that can run independently, your device can kind of run both of them, right, instead of sitting idle waiting for the next thing. So this is your right answer. Let's look at this. Faster data processing by improving synchronization, not really. Reduces kernel launch overhead, not really, because again, kernel launch overhead is kind of the overhead you pay to launch a particular kernel, which is still going to be there even if you have multiple command queues. Improves data sharing across multiple command queues. No, like I said, these are independent, right? That's why we are separating them out into multiple command queues. So basically, you can form a pipeline for better utilization. That's what helps. We'll move to the next question. Consider the reduction kernel to find the maximum of a given dataset, 1048576 elements. The code is like this. The kernel is called max. Shared int sdata 2048. TID is threadidx.x. I is blockidx.x into blockdimension.x into 2 plus threadidx.x. sdata equal to gidata plus gidata I plus blockdimension.x. You have a sync threads after that. Then in a loop where s goes from blockdimension.x by 2 till greater than 0 and you shift it by 1. TID less, if TID less than s, state of TID equal to max of state of TID, state of TID plus s, and then again you do a sync threads. TID equal to 0, G of O data of block ID of X equal to S data of 0. This is your reduction kernel. Now we are applying thread coarsening with a coarsening factor of 4 for this kernel. The maximum size of a work group that can be launched is 1024 work items. The kernel invocation command is given below. What is the content of the arrays? Global work size and local work size. ERR equal to CLNQ ND range kernel. Commands max coarsened 1 null, global work size, local work size 0 null none. So you have 4 options for the global work size and the local work size. I'll pause here for a minute and a half. I'll go back to the kernel and then come to the options. I'll go to the options now. We look at the answer now. The answer is C, 26214411. Local work size is 102411. So local work size is pretty clear because the maximum size for a work group is 1024. So you cannot go to 2048. And then your global work size is your total number of threads. So what is the size of your reduction kernel? This basically converts to 2 to the power of 20. Now given that your coarsening factor or thread coarsening in particular is 4 or 2 to the power of 2, your work size becomes 2 to the power of 20 divided by 2 to the power of 2, right? Because you're basically making a single thread do the work of 4 threads by coarsening it. So your global work size will become 2 to the power of 18. That basically comes out to this. So your correct answer is C, right? So if you only calculate global work size also in this case, you will only get C as a valid option. In case you calculate global work size and you have multiple valid local work size options, look at the maximum valid local work size and then choose your option. We'll move to the next question now. The execution of an operation in a CUDA stream is always synchronous with respect to the host. True, false. So the answer to this is B, false. I think it's very clear why. We already spoke about how commands are asynchronous, right? So you can issue a command, but you don't really, that when the command returns to the host, it doesn't mean that the operation has completed. So in that sense, it is asynchronous. So the statement that it's always synchronous with respect to the host is false. Move to the next question. Device fission can be useful in the following cases: dividing CPU-like devices into smaller subdevices, build a portable and powerful threading application based on data parallelism, merge multiple devices to increase parallelism. You have four options that are various combinations of this. Let's look at the answer. Answer is B, 1, comma 2. So already we understand the term device fission. We went over that. It refers to dividing CPU-like devices into smaller subdevices. Option 2 says to build a powerful and portable threading application based on data parallelism. Yes, you can also do this with device fission. So both of these are correct options. Merge multiple devices is kind of the opposite of divide devices, right? So this is not this is not pertinent to device fission at all. So options 1 and 2 are correct, which means B is your right answer. We'll move to the next question. The given DAG with 3 kernels in this one on the right, the edge denotes that the output of the parent node is the input of the child node. This one, for example, right? B is the output of K1 and the input of K3. The kernels are executing in out of order fashion. Assume the target hardware has one AMD CPU and one AMD GPU. All the inputs and output buffers are of the same size and dimension. Q CPU and Q GPU are the command queues for CPU and GPU. Data size is the variable for data size. DA, DC, DE, HA, HC, HE are the CL buffers and memory at host side respectively. Global work size and local work size are the work size variables. E1, E2, E3, E4, E5, E6 are the CL events. Now you are given some code here. So two write buffer commands, then three kernel enqueue commands, and a read buffer command, right? Basically, to write this data, execute the three kernels, and then read the output. Now you are given some blanks here which you will be asked to fill. So question 6 asks you for the first four blanks. What are the answers to that? So again, I'll give you some time here. So I'll pause here for 30 seconds and then move to the options. I will move to the code. So keep in mind that in this question you're asked to fill 1, 2, 3 and 4. Basically your two write buffer commands. I'll move to the options now. Okay, let's take a look at the answer. So the answer is 1, 0 null followed by 0 null. So let's take a look at the write buffer command, right? So you're asked to fill these two, basically your number of events in waitlist and the CL event, this one. So for these two write buffer commands, so notice that they write to the Q CPU and Q GPU and your DA and DC and HA and HC, right? So all of these are already populated and these events are referred to as E1 and E2. So now you're asked about what events this one is basically waiting on, these two commands, and how many events those are. So since this is the start of the process, there is no dependency here on copying these two things, right? It doesn't have to wait for anything. And that's why the answer is 0, as in the number of events is 0 for both the write buffer commands, and you pass a null because there is no event waitlist at all. Hope this is clear. We look at a few more questions that are very similar. So the next question is going to be about these two commands. So you'll be asked about the blanks 5, 6, 7 and 8. So let's look at the options for that and I'll give you 1 minute. This should be easier now that we've gone through this part. So I'll maybe go back to the DAG and then pause at the 5, 6, 7, 8. Okay, now I will go to this part. So remember that you're filling these four. We'll go to the options now. Yeah. Okay, let's look at the answer. The answer is D. So the number of events in both cases is 1, and the events they wait for are E1, E2. So the syntax is again given here because this is an NQ range kernel command, and that was a write buffer command. But the parameters we're trying to fill is the same thing, right? The number of events in the wait list and a pointer to the wait list. So if you go back now, we are trying to fill these two, right? Which is the execution of K1 and K2. So let's look at the DAG now. So there is kernel K1 and kernel K2. Now what events should these kernels wait for before they execute? They have to wait for this to be written and this to be written, A and C, which is the same commands that we just looked at. So the events for those two are correspondingly E1 and E2. So this needs to wait for E1, this needs to wait for E2. So in both cases, the number of events that they have to wait for is 1, 1, and the respective events that they wait for are E1 and E2. Therefore, the answer is D. So we look at one other question in this pattern, and as you could have guessed, so the question here is to fill 9, 10, 11 and 12. So since someone just joined, I'll go back to the DAG. You can take a look at the DAG and then I'll go to the options and give you maybe a couple of minutes to solve, and you can put your answer in the chat box. Okay, I will move to the commands. So remember, we are trying to fill in 9, 10, 11 and 12 this time. So take a look at this and then I'll move to the options and give you another minute. Okay, now I will go to the options. We will discuss the answer in a minute. In the meantime, if you have any answers, please post it on chat. Okay, let's discuss the answer now. So the answer is C, but let's take a look at why that is, right? So we are trying to fill these two. So one of them is again an enqueue kernel command, and the final one is a read buffer command. So this is trying to execute kernel 3, and this is trying to read the data back. So now again we are asked for the number of events that both of them wait on and what are the events that they have to wait for. So let's look at the DAG. So for kernel 3 to execute, what does it need? It needs its inputs B and D. So there are two events that it needs to wait for, and the two events are actually, so B and D are generated after K1 and K2 execute, right? So the events that are associated with them are E3 and E4. So this will wait for two events, and the events are E3 and E4, right? So this part should be clear now. Now here you are trying to read the data. So that has to wait for what exactly? It has to wait for the kernel to finish executing, right? Before that it cannot read E. So there is just one event that it should wait for, and that is the kernel execution. The event corresponding to the kernel execution is E5. So the answer in that case is 1 and E5. So the first 9 and 10 is 2 and E3, E4. It has to wait for basically both those outputs, and then the read buffer command has to wait for one thing, which is the kernel execution, and that corresponds to E5. Therefore, your answer is C. Any doubts in this question? Okay, if not, I think we have a few more questions, but we'll take a 5-minute break now since we are done with 1 hour. So we'll resume at 12:07. Okay, let's continue. Consider the same DAG as in question 1. So it's not question 1, it should be question 6 or 5. Basically, whatever showed you the DAG that we just spoke about. The kernels are executed in order fashion. Assume that the target hardware has one AMD GPU. All the inputs and output buffers are of the same size and dimension. What will be the efficient method of synchronization? Command queue barrier for each command, CL flush at the end of all commands, CL finish at the end of all commands, waiting on an event associated with each command. I'll give you a minute and then we'll discuss the answer. Let's discuss the answer. So the answer is CL finish at the end of all commands. So now let's discuss first what are these different types of synchronization and which is the most efficient here. So CL flush says all previously queued OpenCL commands in the command queue are issued to the device associated with the command queue. It only guarantees that queued commands in the command queue will eventually be submitted to the appropriate device. There is no guarantee that they will be complete after CL flush returns. CL finish. All previously queued OpenCL commands in the command queue are issued to the associated device and the function blocks until all previously queued commands have completed. CL finish does not return until all previously queued commands in the command queue have been processed and completed. So this is the main difference between flush and finish. Flush just guarantees that commands in the command queue are issued to the device, but when it returns, it does not mean that they are complete. But finish basically blocks till the commands complete. So when it returns, it means that everything that was queued in the command queue has been processed and completed. Other than that, finish we've already spoken about. There is also command queue barrier and waiting on an event. So command queue barrier ensures that all previously queued commands have finished execution and updating memory objects before subsequently enqueued commands begin execution can be used to synchronize between commands in a single command queue. Waiting on an event, this we just saw in the previous questions. So it enqueues the commands that returns an event that identifies the status of that command. Value of the event associated with that command is set to CL complete when done. So we just saw an example of this, right? So now let's go back to the question and understand which of these would be good for this. So you have the same DAG, which is basically this one, your K1, K2, K3. But now here you had two devices. Now you have only one device. And you're also told that the kernels are executed in an in-order fashion. So do you really need synchronization after each command? Not really, right? Because it is anyway going to execute in order, which means that by the time K3 needs inputs, K1 and K2 would have finished, right? So you do not need either a command queue barrier for each command or waiting on an event associated with each command. You could simply queue all of them. So here what you need is once all of this finishes, you want to kind of continue with whatever is next. right? So if you do a flush, you are not guaranteed that all of these have finished execution. So you need to do a CL finish at the end of all commands. So that is the appropriate method of synchronization. So this really depends, right? It depends on how many devices you have, whether they're executing in order, whether there's some dependency between them that you need to take care of, and so on. So in this particular example, finish is the most appropriate one. Any doubts in this question? Okay, if not, let's move to the next one. Consider an incomplete CUDA code using streams which processes a 2D matrix of dimensions W cross W using a 1D kernel. Matrix is stored using row major format. The 1D kernel processes the array in the following way. For the first row, the kernel processes W elements. For the second row, W by 2. For the third, W by 4, and so on. Fill in the blanks. So this part is for asynchronous transfers to the device. I from 0 to n stream. Offset equal to blank. I element equal to blank. Bytes is the product of I element and size of float. And then you do a CUDA mem copy async from host to device, and I bytes and the direction of this thing as well as the stream is specified. Now here you do the computation and then you do a mem copy again. So this will be pretty much identical to this except that the direction is reversed, right? Now it's device to host, so D and H will be interchanged. Now let's look at the computation. The loop part remains the same. Again you have your offset and I element and you're calling the kernel with these arguments. Grid block, and you're also giving it a stream argument, and you pass it DA, DB, DC and I element. Now the question is, the value of I element on offset are same for all the cases. You basically saw 3 sets of blanks here. It's the same for all cases. So you are asked to select the correct option for I offset and I element. Here are 4 options. I'll give you a couple of minutes. So I'll go back to the code. I'll pause here for a minute and then I'll move to the options. I'll move to the options. You can let me know if you are able to figure out the answer. Okay, let's take a look at the answer. The answer is A, I star W and W divided by 1 left shifted by I, right? So let's take a look at this again. So the question says you have a W cross W matrix and you're trying to process this using a 1D kernel. So the way you process it is the first time you process W elements, then W by 2, W by 4, right? So what you need to figure out is the number of elements and the offset. So remember that the offset is going to increase every time and the number of elements is going to decrease. So the first time you have W, the next time you're told it's W by 2, which this one doesn't do. So you can rule it out. This one you can do. This one also really doesn't do that. So you can rule out this too. So this is the only option, and you can also check for the I offset. So the offset will basically keep increasing each time, right? And that also holds with what the question says. So your elements keep decreasing and the offset keeps increasing. So this is the answer. I think this is the last question. Yes, this is the last question. I'll wait for a minute more in case you have any doubts or questions on any of the content covered so far. Please post it on chat. If not, thank you so much for joining. We have 2 more live sessions and the next couple of Sundays. So look forward to seeing you there. Thank you.